I'm going to talk about having a virtual clock that is across a trust domain. And I guess I need to establish some context here, which is this is for defined trust communications, and its framework has concepts from a lot of different areas of work, and it did grow out of work with NDN, but it's somewhat different from NDN at this point. And one of the major things is that defined trust domains are a type of limited domain, which you can read about in this RFC. And they're very much focused on security and they use something we call the defined trust transport protocol. And an important thing about this is going to the idea of working on limited domains kind of lets us do a lot of things differently than NDN does it. We don't really have to worry about things being globally discoverable or, global identities or any of that. We have, these are closed communities. And the other, I don't want to say a lot about that now. If anybody's interested, you can read up on it, but I'll try to say a few things just to have the context that we do have rules that make a communication schema, and those are integrated into the transport. And that's, how it works. And the rules also give the format for legal member identities, and then those identities are distributed as a chain of trust, and they can include things like capabilities and attributes, but all of that has to meet whatever definition was in the rules. The thing I want to say is that the details of this virtual clock are specific to defined trust communications, but I think that some of these ideas about using collection-based communications can also be applied in NDN. So I'm kind of presenting this as, hopefully something that can make people think about, oh, can I use some of that to handle some problem I have? And I just want to show this quickly. Anybody interested can look later. This is sort of a block diagram of DEFT, the transport protocol. And we have an API that is a pub sub. So anyway, that's the basic concept. So let me talk about the problem that we have of domain-wide clock synchronization. And I've already mentioned that DEFT has a sort of publish-subscribe API that looks like MQTT, and it has a lot of internal collections that are part of its infrastructure. And each of these collections is managed by an instance of SyncPS, which is a sync protocol. And that idea is similar to having a sync protocol in NDN. And what SyncPS does is it sends and receives the publications, but they're wrapped in its own PDUs, and then those are exchanged with the system transport, which could be UDP, TCP, IPv6. PDUs are hierarchically named, and the prefix has the domain identifier, so everything's applying across this one trust domain, and it has the collection name. And publications are time-stamped. We use this to prevent replay attacks primarily, but there are other reasons also. And this requires a shared notion of that publication clock throughout the trust domain. So in doing some testing and deployment, Scott Gray from Operant found that many of the devices in the field don't use NTP, and they don't really want to because they don't want to use external communications. We decided that the solution was to give DEFT an integrated, self-contained virtual clock that was calibrated to the kind of accuracy we need, which isn't terribly accurate compared to what you might be used to for NTP. And of note might be that the DEFT publications and PDUs are both similar to NDN data in format, so maybe that will help with some context. So anyway, this is this upper part is kind of what DEFT looks like. And on this first row, this stuff is all kind of directly used by the communication schema. And these are over to the right-hand side are all the various kind of infrastructure things that get done. So when you see the sort of separate lines that go into the system transport, those are all from different collections or different sync PSs. And I also want to note the lower piece that a trust domain can span different subnets. And here I tried to show that by a different color. And those can be connected by something we call relays that can go between different subnets. The different subnets could be, different types of media. It could be Bluetooth and Wi-Fi or something, but it could also just be different subnets that are, defined in other ways. But the important thing to keep in mind is that not all the devices on a subnet could hear each other directly. And so I put these dotted lines in to kind of show that maybe these are the only things that hear each other directly, but SyncPS will, mesh things and move it through the system normally. And that's the environment we're dealing with. There's a lot of ways to calibrate clocks in a network. People are probably familiar with internet-based approaches like NTP, and those access globally accurate time servers. And then there are some sensor network approaches that I took a look at, but they seem to designate or elect primary sources and build trees to distribute reference times. And then they'll do things like estimate skew and offset parameters relative to that reference. And for us, neither approach was attractive. We wanted something that was self-contained and robust to communication topology changes and failures. And we can take advantage of our environment to do things a little bit differently because we don't really have to track the actual time, and we don't even have to stay monotonic over the history, right? We can move it backwards if we need to. And our relative precision doesn't necessarily have to be that great because it relates to the lifetime of our publications, and our normal sort of thing that we use is a lifetime of 1 second. But I think we can do better than half a second. I can show this at the end, but we need to do further testing. So also, using our collection-based semantics, we can completely ignore the idea of skew estimation because we just sort of periodically synchronize the offset and everybody, gets back on track. What you want to do in order to do that is update your collection with each virtual clock, and so that before you would drift out of tolerance, you would see it. And for normal clocks, if we do this on the order of 10 minutes, we should be fine. Just kind of a little bit more of an overview here is that the way things work for us is the certificate publications that make up the identities have lifetimes that are normally on the order of hours to years. So we don't usually run into any problem with clock differences there. So what happens is right after that, we normally go into things like key distribution and then, go into exchanging application messages. So it's right after that certificate publication, which we call joining, is that you kind of need to do something about the timing. And so that's where we've inserted this virtual clock distributor. And it uses a collection and these other things that I already said, but it was really important that the algorithm is completely distributed between members and that there's no use of external servers. And one of the things that we want to be able to do, which I will freely admit is not implemented yet, is that members that have access to precise clocks, we could designate them with a capability in their identity that says, this particular member has a really precise clock, and in that case, we give preference to that clock. In doing the calibration, we decided to do it within single hop reachable neighborhoods instead of, like when I showed that thing earlier, it doesn't happen, the calibration doesn't happen instantly across the whole network. We do it within the single hop neighborhoods, and then we sort of propagate it gossip style. We do this by changing the parameters in SyncPS. The SyncPS is for this collection, so that instead of forwarding something from somebody else or sending it on, you just don't do that, and things also don't live that long. The way that it works is that members periodically send their virtual clock out as timestamps in the publications, and again, to keep them fresh and minimize the delays, they're only received by members within that single hop, and they can't be resent, and they're not valid very long. And that periodicity should be short enough so that, we don't let things drift too much, but we don't want to be doing it all the time and flooding the communication links, as we've seen in the last talk that can be a problem. And these publications contain the number of neighbor members. So it's like, how many people do I see in my neighborhood? And they also kind of keep track of how many are in tolerance with that sender's current virtual clock. And then there's a state. So a newly started member, it sends out its virtual clock, and that's at that point, it's identical to its system clock. And it will say, I have an intolerance neighborhood of 1, which is just me. I'm in tolerance with myself. And if any members get a clock publication with a timestamp that's farther away from their local virtual clock than that tolerance, they go into a calibration cycle. And they save the differences, and they keep track of it by the sender, and they go into this state where they're going to keep sending sets of their own clock publications, and then they're going to process these. And the set size should be on the order of maybe 3 to 8, because of the way this is done, you could lose things, right? You don't resend anything. So we want to make sure that at least some samples get through. And we're always taking, maybe this is on the next slide. What we're always doing is taking the minimum received value so that we can kind of, factor out some of that non-determinism of processing and transport delays. Then members go ahead and do this offset computation sort of a short delay after they've finished sending their set of clock publications. And then you kind of keep doing rounds of sending those sets of clock publications and computing offsets until all of your neighbors are within tolerance. And we take our time here, like we move to this state 1, and we have to stay there through several rounds before we go to 0, which is our calibrated state. And any member that isn't in calibration keeps incrementing its state. And the reason we do this is in a fully connected network, everything can work great, right? But when we have more complicated networks, like I showed back on the earlier slide, you have different parts kind of calibrating themselves, and they're going to end up having slightly different offsets, and you don't want to be constantly starting back from 0. So it's kind of a balance, again, between not starting over all the time, but we don't want to take too long to converge. So again, this is another slide that probably is just here for anybody to look at afterwards if they're interested. But this is the way that the offset computation is done. And again, we go through until everybody is calibrated. And then I wanted to point out that we do something a little differently in the relays. If you remember, what I'd mentioned earlier is that relays connect different subnets. So in order to sort of figure out how to correctly treat them in this neighborhood approach, they sort of act like a single node in that virtual clock distribution. And what happens is all of the clock difference samples sort of go into the central part of the relay rather than each individual transport doing the work. And then the calibration algorithm happens at the relay level. And then that final value of their offset just goes out to all the attached DEFs, the attached transports that are in each separate subnet. The other problem that we have that comes a little more clear when you think about relays, like these pictures, is that they could have non-negligible delays. If you're sitting on a multicast network and local network in general, your delays aren't very long, but in going across maybe the country or something, we really would like to remove those delays before we take out clock differences. So to this end, we have our own RTT estimator for this purpose. And we mean something maybe a little different by RTT than what you think of as a round trip time between two different entities. We're thinking of the round trip time of the neighborhood. I mean, the neighborhood might be just two entities, like it would be across a TCP link. Looking at those delays some more, we have processing delays that are from our cryptographic signing and validation, and then we have the transit delays, and they both add noise. And we approach those in two ways: that clock differences are always quantized and we always round down, and that quantization value should be maybe a little bit larger than the normal transit and processing delay for a broadcast network. So we can use our round trip time estimator. So there's two ways we can do it. Like, we can just sort of guess and set that normal transit processing delay, or we can use our round trip time estimator and then do things like use it to come up with a quantization. And if it's a larger value, like maybe across a TCP link, then we can just subtract it from the clock differences. And this is just how we do the RTT. I think what's nice here is using these collection semantics that are really map nicely onto broadcast networks. You can do some things in a slightly different way. So all the members are subscribing to both ping and echo publications, and it sort of randomly a member will send a ping publication, and it does select a particular neighbor to respond to it, and it sticks that ID in the publication name, and then it saves its current time. And then everybody gets that ping, and they go ahead and kind of save it if it's not for them. And if it is for them, they send the echo. But everybody can overhear that echo, so everybody can, get an RTT estimate for the neighborhood. So it's just, something that you get to think about when you're working in sort of a broadcast collection-based mode. I did some preliminary testing, and yes, this is all on a single machine for now, but I wanted to see if it could work at all. So I've got 8 members, and they're emulated on a single machine, and RTTs are kind of on the order of 2 milliseconds. I'm using 5 millisecond quantization and a 20 millisecond difference tolerance. And I want to calibrate to differences that are plus and minus that quantization, and differences that exceed the tolerance will start calibration again. So the way I did this is every member gets a random offset at the initialization time, and then it gets a sort of randomized drift emulation. And this is, it's a little extreme because normally we expect it to be around 40 microseconds per second. And, hence the idea that 10 minutes or so could possibly work. These large periodic perturbations are going to make my experiments clock move a lot more than we'd expect in normal use. And what I can do, what we have built into our code is sort of a way to emulate 3 different types of connectivity in a broadcast network. We can have full, where everybody hears everybody else. We can make 2 overlapping groups, or we can make a sort of a linear arrangement where, you only hear the next person in line. So in order to do these, show these results, what I've got is every member publishes a log message that contains its virtual clock when it finishes calibration. And then we can just listen to this and save it, and I can create the plots that I did here. I then subtract that virtual clock from, the system clock, the real system. Remember, this is running on one machine. And the system clock is contained, as I said here, the DCT watch timestamp. And I guess DCT watch is a thing that we can use to listen to our DEFT packets on the network. And this is kind of a cool thing. And Van Jacobson wrote this so that we could find out we could keep an eye on what's actually happening. So I have to thank him. By doing this, then I can plot the members' differences and from the system clock. So the first calibration convergences took about plus or minus 6 seconds for the fully connected and for the 2-group version, but they took plus or minus 30 seconds for that linear arrangement. And these delays include all those built-in wait delays, and those might be able to be cut down, but I'm not sure if they really need to be or not. Okay, so here's 8 members that are fully connected through a broadcast. And this upper plot is just showing you how different they all started out, and then they kind of go along and became fully connected. Then I kind of blew this up here. And I just wanted to point out that all 8 of these actually have the same offset after the first calibration. I could tell this because there's some other data I was using to see it, what it actually was. But the difference here is which is maximum of 14 milliseconds. It's just variations in our processing and capture time. So this is where you split them into 2 overlapping groups. And this is just, you do this with a compile flag. And again, here's a detail of the 2 groups that they end up, staying quite close together. So they did converge. But these ones get to be a little bit more fun. This gets arranged in a line, and you can see what's happening here. If you look at the upper one, it's okay, there's all this stuff, and then we get things that are closer together. But when I blew up, the upper part, you can see some of these members pass their calibration, so they think they're calibrated, then they hear from others, so it starts the calibration going again. So that's why we get multiple logged messages, and the differences did stay under 15 milliseconds, which is what we wanted. Then here's one where I'm connecting through a relay, and I started the right side members and their relay first, and then started the rest. And you can kind of see what happens here when the right-hand side starts. You've got all these different values, and then they, pop up and converge. And then the left-hand side starts, and it kind of moves things around again. One of the things I want to say that maybe I didn't emphasize so much before is that I started out looking at the median value, but I really had this goal that you know, what we really want to do is converge quickly, and we sort of want to say, if somebody new comes along and joins the group, we kind of want to bully them into having the same clock as everyone else. We don't want them to be able to pull us in some different direction. And so over time, I started playing around more. I use a mode rather than the median here, and that worked a lot better, because when I used the median, it often would not converge properly for the weird things like the linear one. You'd get things that were pretty far off, and that was not acceptable. So this is looking at a detail of that relay setup. And again, we can see all the kind of weird behavior because the other side starts and things have to, the neighborhoods have to kind of get it together. So the next steps are larger scale testing, which will be coordinated by operant networks. We might do a little bit of testing with multiple machines before that. It just depends on what else is going on. And the really important things for us to look at is these convergence properties. Do they work well as we scale up our networks and do weirder things with the connectivity? And, does it stay robust? And also just investigating some of these parameters that that are kind of, there are reasons that I picked them, but they're slightly picked out of a hat until you really get to a real network and see how it works. So can we cut down some of these delays? What do we need to do? And also I need to integrate that round trip delay computation into the determination of the quantization, which I'm not really doing now. We're just computing it. And I also want to integrate the use of that clock capability that says, here's something that's a lot more, who has a reliable clock. And finally, iterate that core algorithm if we need to. But, we're hoping that this will be a little bit of a team effort when we get to this point. Right, Randy? Good. Okay, that's it. I'm done.
I just wanted to add that this, if you step up a level, this is something our customers wanted, right? This isn't like Kathie and I were sitting around going, what would be cool? We went and deployed our network tool on some large solar sites in Texas, and they didn't work. And we're like, wait a minute, they don't have any source of time here. They're just whatever system clocks are. They don't connect them to NIST. So we said, just hook them to an NTP server so they're all synced. And they're like, we can't do that. So they don't want a network connection external. These things are regulated cybersecurity sites, and every connection costs them effort and time and is a potential hole. So, we wanted to build a system that didn't require external access. So the right way is this decentralized approach, not because our customers don't trust NIST to tell them what time. They just don't want to connect to NIST. And so you can get to the need for certain architectures like decentralization for reasons that weren't apparent when we started it. And it was all news to us. Like, this was last fall. We were years into this project, and they're like, we can't have time. What? So it's just interesting when we talk about what drives adoption of these kind of architectural shifts. It's not always obvious till you put it out in the real world. So just food for thought for maybe how to move things forward. And what Kathie's done here is pretty cool in the sense that a lot of our customers now, they'll be like, I get a clock for free with my networking. I don't got to think about that. That's a value. Right? So anyway, it's been a good thing, and we're looking forward to rolling it out to the customers, because we literally have sites out there that are drifting and will eventually run out of tolerance, and we have to get this in their hands before the clocks get so out of sync that the various publication lifetimes don't match. So work under pressure, right, Kathie?
Well, maybe. You mean that you didn't just present this to me as a fun problem? I mean, I'm crushed. It is fun. I should say this is a very fun thing to work on, and I hope you guys are all having fun with the work that you're doing too. This idea of pulling yourself out of thinking in terms of client server or A talks to B is actually really good for the brain. It's kind of fun. So.
In your environment, how do you bootstrap time on each device? You have to manually configure when you start in?
Yeah, like there's an installation process, but one way to think, these big solar sites now, they're huge, right? But there's nobody there. So a technician will typically show up every couple of weeks in their truck to do anything that needs to be done. If they're putting one of our gateways in, they set the time, but then they walk away. So it's that's why this convergence and re-syncing is important, and this realization that absolute time, we didn't need NIST precision atomic clock. We needed agreement amongst a bunch of peers that we're all in this same time zone, right?
Yeah.
A little different problem.
Thanks, Randy, for that explanation. That's very important. My question actually leads to the next one. That is, what is the scale of this virtual clock?
What do you mean by scale?
That is among how big the system you have to synchronize up.
Right now it's small, but eventually it will be tens of thousands of things, but they'll be in sub-trust zones.
Right.
So probably 100, I'm guessing, in any one time/sync zone. And they'll be hierarchically structured sync zones.
Will be hierarchically structured trust zone.
Probably 3 levels.
Okay. Yeah, I think I had some scalability discussion that could be informative.
Well, we're quite concerned.